It's still published, but when I look for it, try to, yeah. Okay. Leon? This is the last one. Oh, I think you recorded it. It's not. Is this live? It said that it's live. This will come up like this. Okay. Nothing follows you. Stable. Sorry. Let's see if it works. Yeah.
Thanks, though.
Thank you.
Okay, I would say let's start. Okay, first things first. Each of you already should have their grades for homework 2. Is it correct? Yes. Okay, perfect. Today I'm going to continue the lectures on generative models that Burton started like almost 2 weeks ago.
Do you mind drawing up the light?
Yeah, you're right. Okay, this one. Better? Okay. Okay, so what we saw up to now, we saw the differences between supervised and unsupervised learning, right? So supervised learning is where basically we have the labels and we can learn something from those. Unsupervised learning is when we only have the raw data and we don't have any additional information. But we still want to learn some kind of structure from the data itself. Okay? Then we talked about generative models. We talked about the very early ones like pixel RNN and pixel CNN. And last time we talked about variational autoencoders, right? So variational autoencoder, just to summarize quickly, is a neural network that takes a data point as its input and returns a vector of means and a vector of standard deviations from which we sample and from which we try to reconstruct through the decoder the same input, right? The main differences between pixel CNNs and VAEs is that pixel CNNs define tractable density functions, right? So we can learn the probability of the data directly, but only when this is tractable. While VAEs actually can define intractable density functions like this this integral, but we cannot optimize directly. We have to actually optimize a lower bound. So if you remember, we derived the lower bound last time. If you remember, if you understood, we can only basically maximize the lower bound of this probability distribution, but not directly treat and define the probability distribution. Does it make sense? These differences? Right? Some signs of life?
Can you give an example of the differences between these two so that it will be useful?
I don't have an example actually. It's kind of hard to come up with an example. But I mean, VAEs are used, for example, for like probability distributions over like pictures of faces, right? So, like, you want to define some features, for example, but what are the probability distributions of the features? Like, how can you define the features? How can you model the features directly? So you use a VAE because the VAE finds its features like on its own and models this this probability distribution given like a prior and the data itself. It's really a little hard for me to come up with like better explanations, but like just the main difference that I want you to remember is that pixel CNNs can only do stuff that is directly tractable, while VAEs take probability distributions that are not tractable and simply maximize the lower bound of these distributions, just because they're not tractable directly. That is the main difference. That's it. Okay? Okay. But sometimes we are not, sometimes we don't actually care about the probabilities themselves, right? We are interested in the probability distribution, but only in the way in which we can actually sample from the probability distribution. We are not modeling the probabilities themselves. Does it make sense? Sometimes we are only interested in being able to sample from this probability distribution, not necessarily on its probability. This is exactly what GANs do. They don't work with explicit density functions, right? But they are great at creating samples from the probability distribution. Okay? So let's talk about GANs. Before talking about GANs themselves, I want to talk a little bit about game theory and some definitions in game theory. I'm not going to go into like deep math, just to understand where GANs come from, right? Did any of you take any class in game theory or stuff like that? You're a mathematician. Are you?
No, we're from economics.
Right. Actually, a lot of these concepts my wife explained to me. She has a degree in economics. So, okay, game theory is the process of modeling strategic interactions between two or more players in a situation containing a set of rules and outcomes, right? So, this is basically a game. A game is nothing more than a set of rules where, like, players that we will define later can define their strategies so to obtain a gain or to avoid a loss. Okay? So, some definitions. The game itself is defined as a set of rules. We have a player, more than one possibly. Players are defined as strategic decision makers. Of course, in game theory and like in math in general, we have to assume that the players are completely logical, right? Otherwise, it would be pretty hard to put like too much randomness in what they do. So a strategy, which is a plan or actions that players can take given the state of the game, right? Payoffs are exactly this. Like payoffs are payout for each action. So each time an action is taken, there will be either a gain or a loss for the player itself, right? And the player will move based on these payoffs. In any game you can think about, what we want to do is maximizing our payoff. Who wins the games? The player that has the maximum amount of payoffs at the end of the game, right? And then there is an information set. So it's the information available to players at each given point in the game, right? For example, there are games where we have, for example, in chess, right? In chess, at each point in the game, each player knows completely the state of the game, the strategy of the opponent. There are other games where we don't know, like we don't have a full view of the strategy, for example, of our opponent, right? If you talk about, for example, Texas Hold'em, right? We have 3 cards on the table, and we know those 3 cards, but we don't know the strategy of each other player, because the 2 cards that we had in our hands, we know ours, but we don't know the ones of the other players, right? So the information set is is basically the amount of information that each player has at each point. So there are different game types, and I will tell you just a few of the categories, because there's lots and lots and lots of them. Okay, so we have the first one that I wanted to talk about is this. So cooperative versus non-cooperative games. So there are some games in which we can form alliances in order to maximize our payouts, but there are non-cooperative games in which these alliances are not allowed, and so each player has to play on its own, right? So basically, we either maximize our payoffs together, or each one is on our own. Do the examples make sense?
Sure. Yeah.
Right? So we have symmetric versus asymmetric games. Symmetric games are games where each player has the same set of moves, the same set of goals, and so even if we just switch the players, the game still can continue, right? The game is still the same. The asymmetric games are the ones in which either the 2 players have conflicting goals or different goals. Like in the example that I put here, there is the lioness chasing an antelope, I think it's called in English. Whatever it is, it's a horned animal. So, of course, this game makes sense because the lion wants to eat and the other wants to just run, right? To be able to live another day. But if you switch the players, the game doesn't make sense anymore, right? Like the antelope, why should the antelope chase the lioness? Doesn't make sense. It's asymmetric because their goals are completely conflicting, right? So we have perfect versus imperfect information, which is the thing I was telling you about. So in perfect information, each player knows the state of the game and the strategies of each opponent at each point in the game. So each player has a full view of the state of the game. While in perfect information, there's only a partial view of the other player's strategy, and so it becomes more of a bet, right? We have simultaneous versus sequential games. So simultaneous games are, of course, games where all players make their moves at the same time, while sequential games are turn-based, right? So, for example, for whoever studied AI, right? This Minimax game is very common in certain fields of AI, right? Where you have some some elements that want to maximize a variable, while there is another element that wants to minimize the same variable. Since they kind of go in turns, if you know who starts from the very beginning, you can tell how the game is gonna end and back propagate basically through that. But yeah, just this is about simultaneous and sequential games. And then there are like the zero-sum versus non-zero-sum games, right? Zero-sum games are games where at each point in the game, the sum of the payoffs stays always the same, right? So in the case of like the cake, so if one of the players has more cake, it means that the other players have less cake, right? And the sum of the payoffs remains the same at each point, right? While in non-zero-sum game, technically everybody could win. These are games where each one wants to maximize his or her payoff, but this maximization of the payoff doesn't necessarily mean that someone else is penalized. Okay? So just as an example, in Pac-Man, for example, let's like defining Pac-Man in like game theory terms. We have the game, which is the set of rules, right? Each player simply moves one square at each time, and each player cannot go through the walls, right? Defining the players, we have only two types of players, right? Which are the players in this game? Ghosts and Ghosts and Pac-Man. So I just put down some like made up payoffs for Pac-Man, just for sake of the example, right? So at each point, Pac-Man has to move one square. So Pac-Man has to decide where to move, right? So he can decide to move based on like on this payoff. So if Pac-Man hits a circle, it's a gain, right? It's a big gain. So I gave it like +10. If it gets closer to a circle, it's +1. But if it gets closer to a ghost, it's -5. And of course, if Pac-Man gets eaten, the payoff is -infinity, because at that point, the game is over and Pac-Man cannot do anything anymore. Pac-Man simply lost, right? So that is the main thing that Pac-Man wants to avoid. Then, like, whenever the ghosts are vulnerable, eating a ghost gains more points than just eating one circle, right? So I get like +20, and that getting closer to a vulnerable ghost is +5. The payoffs of the ghosts are similar but reversed, right? Because like getting closer to Pac-Man is a +1, but getting closer to Pac-Man when Pac-Man is invulnerable, it becomes a cost, right? Getting eaten by Pac-Man is -10, and of course eating Pac-Man is what we want, correct? So this is a non-cooperative game because of course it's actually adversarial, right? It's zero-sum. Someone wins, someone loses. It's asymmetric because the goals of the players are different. It's perfect information because at each time all the players know where the others are, right? So Pac-Man knows where the ghosts are and the ghosts know where Pac-Man is. So the information is perfect at each time. It's simultaneous because everybody moves at the same time. And yes, it's a zero-sum because one wins and one loses. So in 2014, Ian Goodfellow, which was a PhD student in Toronto, I think, he had this idea of applying game theory to generative models, right? So he set up this networks so that they would play a game one against each other. So this is the setup. We are given a set X of real data points, right? We want to construct a generator that can sample from the same probability distribution of X, right? So we're not trying to model the distribution so that we know the probabilities, but we want to be able to sample from this probability distribution. This is the goal of the generator. So some of the most used data sets for GANs are these. So we have MNIST and Celebay. I trust you already saw these. MNIST is kind of easy. It's kind of an easy data set to work on, also because MNIST, for each pixel, we basically have just a classification, right? It's either 1 because it's white, or it's black because it's background. But it's very, very difficult for even us to define what the characteristics of the probability distribution of pictures of faces are, right? Like, we know how a face should look, but all the subtleties of the features are very hard to describe in mathematical terms, right? So let's talk about how this game works. So we have two players, right? We have the generator, whose goal we already said, right? It's to generate stuff from the probability, like samples from the probability distribution of X. Both of and the discriminator, who will try to catch what is real and what is generated, right? Both of them are modeled as neural networks. Usually, the generator actually expands the dimensions of the input, while the discriminator will shrink them. So usually in the generator, you find transpose convolutional layers. Do you remember what they are? Do someone know what the transpose convolutional layer is? I need a yes or a no.
Is it like enlarge from the low dimension to high dimension to?
Sorry?
Is it just to enlarge from small to large?
Mm-hmm.
That's for segmentation, or?
Is it a question?
Yes. Segmentation. That's for yes.
For segmentation. You're talking about the transpose convolution?
Yeah.
Transpose convolution is an operation that is designed to be the opposite of a convolution. Okay, so you usually, with a convolution, you start with something. Let's say a convolution with stripe 2, right? You start with an input and you end up with an output that is half in each of the directions of the input. So if I have an image and I convolve with stripe 2, I will obtain an image that has like a fourth of the number of pixels of the image, right? A transpose convolution is designed to be the exact opposite. I start with something that is smaller and I end up with something bigger. It's like a transpose convolution is basically just the inverse of a convolution, simply put. It's a little bit more difficult than that, but this is what lets us design networks that can expand, right? Sorry, convolutional networks that can expand, because we can always expand with fully connected layers, right? But fully connected layers don't have that assumption of what a neighborhood is that an image usually needs, right? So the transpose, like, the generator usually uses transpose convolutions to expand from a lower dimensional Z to the space of the images. That's it. Okay? Any questions?
So Z is also learned by the model, right?
No. Z is the input to the generator. Because when we generate, we need some distribution that is easy for us to sample from.
Right.
Right? So we use, usually we use random noise, right, from a normal distribution or a uniform distribution, right? Where each entry of this vector is actually taken from a unidimensional normal distribution. Okay? So basically we obtain a vector for which each entry is actually independent from independent from all the others. Right? Which for us is very easy to, like, it's very easy for us to sample. So what we want to do is actually transform this distribution that we know to the target distribution that is the one that we cannot directly manipulate, right? So starting from this Z, which is a known distribution, we obtain this G of Z, which is a generated image. Yes?
So when you use the uniform distribution, when you use normal distribution?
It depends, and in my experience, it doesn't really make a big difference. The normal distribution is just better because you are not, usually it's better mathematically because you are not cutting off parts of the space, because you know that like in a uniform distribution you have a uniform distribution in a range, but the probability of being outside of the range is all zero, right? While in a uniform distribution, the whole space has at least a very, very small probability of coming out. So that is usually the main difference. I've seen the normal distribution being used more than the uniform. Yes, the normal is used more than the uniform, but in my experience, it doesn't make a huge difference. So, plus there are like, yeah, I mean, there are some mathematical things to take in account, but yeah, that's pretty much it.
Is there like a lower like probability than, like, say, like 0.002 or something below which it doesn't even matter? It's same as like, having like a zero or something.
Sorry, can you repeat the question?
So the noise, each of the noise has like some probability.
Yes.
Is there like a lower bound for the probability where below which it doesn't matter what probability it is, it is equal to 0?
No, but it doesn't really matter because, like, remember that the training is probabilistic in a neural network, right? But the product of this neural network is always deterministic. What is important is the numbers inside these, but not their probabilities, really, right? So the probabilities are not very important, especially because in this case we are only trying to sample from the probability distribution, but we're not interested to sample from the target probability distribution, but we're not really interested in the probabilities themselves, right? So does it make sense? Did I answer your question? Okay. Any other question? Okay. So we obtain this G of Z, which is a generated sample that of course it's in the space of X, right? So for example, in MNIST, if you want to generate new handwritten digits, right? What we do is we give you, either a 64 or 100 dimensional Z in the generator, and the output will be a 28 by 28 image, like the MNIST digits, right? So then we give these generated images, like a mini batch of generated images and a mini batch of real images, to the discriminator that has to return, the discriminator has to return a probability for each of the samples, right? So the goal of the discriminator is actually given a 0 if it thinks that the sample is generated, and a 1 if it thinks that the sample is real. Okay? So, any question up to you?
Yeah, 2 questions. The first is that, well, we have multiple X, right? But we currently only generate 1 example. So, do we need to compare?
We usually generate more than 1, right? We generate a mini batch
of pictures, then we compare with every point in X. So I mean the discriminator, right?
Yes.
And it will compare the generated picture with all the data in X, or just with a subset of real images.
I'm sorry.
Oh, okay. So now we have generated a batch of images, right?
Yes.
And the discriminator will compare these generated images with the real pictures. And
yes.
But we have a lot of real pictures, right?
Yes.
So do you compare
you choose a mini batch at random
from the real pictures?
from the real pictures. You choose a random.
Okay.
Let's say that you have your mini batch size is like 10, right? So you give 10 generated images, right? That you choose at random because this is chosen at random,
Right.
right? And 10 images chosen at random from the real distribution. Okay? It doesn't do a direct comparison between them, right? Because the discriminator simply processes each sample individually and just returns a probability that, in its opinion, it's fake or real, right? Does it make sense?
So just to summarize, the generator is trying to figure out how to make images that are so similar to a real photo
Yes.
that it tricks this discriminator.
Exactly. The generator wants to trick the discriminator, creating images that are close to the real ones, and the discriminator wants to actually catch the differences between the real images and the generated ones, right?
Why can't we directly use a very well-trained CNN for a discriminator? Because discriminator, whatever discriminator is doing, is the same task as of similar to the classifier. If we have a very good trained, like very well trained CNN, it will do the same task.
Very well trained on what?
Okay.
Because that is the trick. The problem is that the discriminator and the generator have to learn together. Because if you train a discriminator and it can catch stuff that is generated from one generator, right? That discriminator is trained and it won. Then you train a new generator, but the new generator will not generate necessarily stuff that is close to the first generator, right? The discriminator learns stuff that is it learns features that are connected to the features of this specific generator at each point.
Right.
so that this generator will actually modify its own parameters to make better and better images. Does it make sense?
Yeah.
Does it make sense for everyone?
Yeah, so that means the generator always generates the meaningful real pictures out of, say, nothing, because it is Z is always randomly initialized, right?
Yes.
So that's quite different from the, say, VAE, because in VAE the Z is some meaningful features, but here Z is always
Yes.
random.
Yes.
That sounds like magic.
Yes. But since they are playing this game, right, the generator has to learn something from the discriminator loss itself, right? And so it learns the features, but the problem is exactly this, that these don't make any sense to us. Even when the generator is totally spot on and model the manifold of the real data, this Z is not a meaningful embedding. That's why I was trying to explain embedding last time, and I shouldn't have. But these features to us don't tell anything. For example, in a VAE, sometimes you can, for example, if you train on MNIST, you can see some clusters where, for example, you could have, you could see some clusters in the embedding where you could have, for example, clustered together the zeros or the ones, right? But in this case, if you try to look at this as an embedding, everything looks like all just entangled together, all mingled together. It doesn't make any sense. You would see like a rainbow of colors that it looks like noise. Oh, you.
Is the output of Z binary, or is it a...
No, it's a probability. It's a probability, sorry.
So it's bounded by 0 and 1?
It's between 0 and 1. You usually use a sigmoid for the output of that, right? So, and then of course your loss though is if it's for the fake one is between the output and 0. If it's for the real one, it's between the output and 1.
Right.
Okay? I'm going to talk about the loss in a second. It's just are we all on the same page?
So the terminator ideas and the generator and discriminators are cooperative. So in the end, they will
Is adversarial.
So they're not both getting better and better.
They are both getting better and better, but they are getting better and better because they try to screw over each other. It's non-cooperative at all. It's actually very zero-sum. Because if the discriminator wins, it means that the generator is losing, and vice versa, right? Other questions? Yes.
So we talked about this example about the mean action of 10 real images being generated once. So how does the discriminator decide which of these generated image to compare to which of these real images? Or is it done against every single real image?
Let me come a little closer because my ears are not very good. Sorry, can you repeat?
Yeah, so you have 10 real images. You have 10 generated images.
Yes.
How does the discriminator decide which generated image to compare against which real image?
This is okay. This is not what happens in the discriminator, right? The discriminator processes each image on its own. It doesn't compare them to the others, okay? Which actually will lead to other problems that I will talk about later. But during the training, the discriminator should learn what features make a real image, right? So at that point, if he doesn't find the same features in one of the images, then he will say, oh, this is fake. Does it make sense? It's not a matter of comparing one image to another image or it's just a matter of learning features of the real data that make them look real. Does it make sense? Okay. Any other question?
I'm thinking how to update the generators. How to actually update the generator? Once you reach the first iterations, and you will go back to generate the new samples.
Really?
I mean, so once you finish the first process, you go back to generate new samples.
Yes.
The whole thing to generate samples. If you update any.
Yes, of course you have to update the parameters.
The
The parameters in the generator and the discriminator, right? I'm gonna talk about how you do it like in a second. Okay? We good? Okay. So, as I said, okay, the generator has to fool the discriminator by generating real looking images, while the discriminator tries to distinguish between real and fake images. Right? That's why it's a zero-sum game, and that's why it's adversarial. Now, this is the objective that we use in GANs, right? If you work with GANs, you see this thing like to become nauseous of this thing. So, since it is an adversarial game, we have the same objective, but one tries to minimize this objective, the other tries to maximize the objective. So, the discriminator tries to maximize the logarithm, like the average, right, of the logarithm of d of x, right, where x is the real data, so samples taken from the real distribution, plus the average of the logarithm of 1 minus d of g of z, where g of z is the samples that are generated by the generator, and they are, of course, they are taken from the distribution of z, right? Like this distribution. Okay? The generator tries to minimize this. So if you actually look at this, if you remember that d only spits out numbers that are between 0 and 1, you will see that the logarithm of those things are always negative. And so when we minimize it, we actually go towards negative infinity, and if we maximize it, we obtain 0. Right? Does it make sense? Okay. So this is how we do it. At each go, at each iteration, we use gradient ascent on the parameters of the discriminator, right? So we have a mini batch of generated. Then we associate a mini batch of real data and just put them in the discriminator, right? We find the loss and we want to maximize it. So we update the parameters of the discriminator, right? Then we generate again, and we find the classification of the discriminator over the new generated ones, and we update the parameters of the generator, trying to minimize this thing. Right? Make sense? It's the usual stuff that we do in neural networks, right? One iteration, we change the parameters. Another iteration, we change the parameters. It's just that in this, we have to change the parameters of the discriminator first, and then the parameters of the generator at each iteration. Of course, we want to change the parameters of the discriminator first, because since the loss depends on D, right? We want D to know at least something at each time to be able to change the generator, especially at the beginning, right? The first iteration, neither of them knows anything. So if I try to change the generator based on this before changing the discriminator, I will obtain nothing, right? So one thing is that if you take a look at this loss function, the problem that we have is that when d of g of z is close to 0, right? The derivative of this loss function is very flat, right? Which is bad for us, because at that point it means that the discriminator is winning, but our change in the parameters of the generator cannot be strong enough, right? So rather than using this loss, we often want to use rather than minimizing this loss, we want to actually maximize this other loss, right? So log of d of g of z, right? So it's just a difference in philosophy, but the effect will be the same, right? So rather than minimizing the probability, how can I say? So instead of minimizing the likelihood of the discriminator being correct, now we want to maximize the likelihood of the discriminator being wrong. It's simply like a change in philosophy, but in the end, it will be the same. The difference, though, is that when the discriminator is getting good, in the second case, the change in the parameters of the generator will be greater because of the slope, right? Because of the derivatives. Any question about this? Did you understand? Okay. So, as I was telling you, like GANs are can lead to different problems. The first of the problems is that they are highly unstable, right? Then there is also mode collapse that I will talk about in a second. Before this, I want to talk about Nash Equilibrium. Do you guys know what Nash Equilibrium is? Except for this definition, which is very quick. Okay. A Nash Equilibrium is just a state in a game where when two players are playing, and a state in which it doesn't matter what the other player is playing, I am not gonna change my strategy, right? If this is valid for all the players, then that is a Nash equilibrium, right? So, a quick example, right? We have two different companies, right? Company A and Company B. They have to decide if advertise their new product or not, right? To make this new advertisement. So these are the gains, right, of the two companies. So if Company A does not advertise and Company B does advertise, Company A earns 0 while Company B earns 200, right? If neither of them advertises, both of them gain 0. Of course, if A advertises and B doesn't, the situation is reversed. If both of them advertise, they will earn both 100, right? So, this can any of you tell me why this is a Nash equilibrium? Yes?
Basically, because your strategy is always to advertise. There's no benefit in not advertising.
Exactly. No matter what the other will choose, each company will always choose to advertise. Doesn't matter what the other chooses. So this is a Nash equilibrium because at this point, we already know what they will do. no matter what. So, should A advertise? Of course it should. Should B advertise? Of course it should. Is there any scenario in which A or B should not advertise? No. That's why we reach the Nash equilibrium. Let's talk about Nash equilibrium in GANs, right? We want to reach the Nash equilibrium in GANs. So it means that point in which neither of them, talking of course about the generator and the discriminator, neither of them will change their parameters anymore. Because, like, based on what the other does, okay? So let's define G star as the perfect generator, right? The generator, like I put this square here saying this is the parameter space, right? The two of them keep moving in the parameter space, trying to screw over each other and blah, 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 blah. So G star, once G star is reached, it means that the generator is completely spot on. The generator produces a probability distribution that is exactly equal to the probability distribution of the real data. Okay? Since these two are equal, it means that D is not able anymore to recognize real symbols from the generated ones, right? Because the manifold of PZ is equal to the manifold of P data, right? So what happens? What do you guys think that happens? What should the generator do when we reach this point? I give another iteration.
Stop.
What?
It's just static at that point, right?
The generator has no incentive to change, right? The parameters will be the same. But then what should the discriminator do?
Also do nothing.
Why should it do nothing? Actually, it's losing. And it knows that it's losing.
Well, of course, given that the Nash equilibrium is reached, according to the definition, no one will have incentives to change his strategy.
True, but it's the generator only now that has reached its equilibrium, right? Not the discriminator.
Okay, so you're saying currently the Nash equilibrium has not been reached.
Technically not.
Okay.
Technically not. I'll tell you what happens. The discriminator at this point tries to find the right space, which occurs, the right parameters, and so it wanders around, trying to look for the right parameters to screw over the generator, which don't exist because of this, right? The right parameters for the discriminator don't exist anymore. So the only thing that at this point the discriminator is, if I give the discriminator one generated image and one real image, and they look both real, but it has to give a classification, right? So what do you think it should say?
They're the same.
That they are the same, or I'll just guess 0.5. With probability 0.5 is real or it's generated. I don't know, because they look the same, right? And that's how it reaches its own Nash equilibrium, right? At that point, the Nash equilibrium is, it doesn't matter what the generator does. I don't know anything anymore. So it's 0.5. That's it. I mean, if you can reach that point with high-dimensional data, like, you're already better than like Ian Goodfellow and everyone else, because this never happens. Never, ever, ever. Okay? You just reach a point where you say, this generated stuff looks good. That's it. The discriminator, in a way or the other, if it's a decent discriminator, always wins. Always. So, yes. This is what I was saying, right? The discriminator simply guesses. Nothing more. Let's talk a little bit more about this objective function, right? So, if we minimize this objective function mathematically is like minimizing the Jensen-Shannon divergence, this one, right? Let's define, do you know the KL divergence? Because I talked about it last time, but not really well. Anyway, the KL divergence is defined as this, okay? Of course, if the two probability distributions are the same, we obtain a probability times the logarithm of 1, which is 0. So, but as we were saying last time, the KL divergence is not really, it's not symmetrical, right? But the Jensen-Shannon divergence is symmetrical, right? Because it's half of the KL divergence of P data and PZ plus half the KL divergence of PZ and P data. So if we are able to minimize this, remember that the KL divergence is a way to quantify the distance between two probability distributions, right? So if we minimize this, it means that the two probability distributions are exactly the same. Okay? So what happens when the discriminator wins? So d of x is exactly 1 and d of g of z is exactly 0. So we obtain the logarithm of 1 for the probability distribution of the real data plus the logarithm of 1 minus 0 for the probability distribution that is generated by the generator. So we obtain a 0, right? If the generator wins, we have d of x that is 1, because the generator doesn't have any power over the discriminator of the real data, right? Correct? But d of g of z is equal 1. And so, at that point, we obtain the same here for the probability distribution of the data, so the logarithm of 1, but for the probability distribution of the generated samples, we obtain the logarithm of 1 minus 1, which is the logarithm of 0, and the logarithm of 0 is negative infinity. Right? Does it make sense? Okay. It was just to like visualize a little bit like what happens when one or the other wins. Okay. So some examples of generated distributions. As you can see, these are from a paper called Conditional Generative Adversarial Networks, which adds a very small tweak to the Z space, right? To be able to avoid mode collapse. The cool thing here is that you can see that these at the beginning and those at the end are actually sampled. All the others are interpolated, right? So you can see that even the manifold that is found by the generator is always smooth, right? So I can interpolate. I can take one sample at random and another sample at random from Z, interpolate between the two of them, and I always find something that is in between the two. I always generate, something that is in between the two. Right? Can you see it? Okay. Any questions? Okay. These images, probably you already saw them lots and lots of times. These were generated last year by a group at NVIDIA. These are very high resolution images generated by a generator that was trained using Celebay. Okay, so do you know Celebay? it's a set of faces of celebrities. Like it has 200,000 something images of celebrities. Okay? I mean, as you can see, all of them actually look like celebrities in a way or the other, right? So, but like, it is really impressive because usually with GANs, you don't want to do something that is like images that are too big, right? Otherwise, it's very, very hard for the generator to arrange all the parameters. But what I think they did was using a stack of generators, right? So the first generator generates a small image from the Z, then the second generator takes this small image and generates a bigger one, then a bigger one, then a bigger one. So, but it looks really good, like no questions about it. This is from, I think it's called LSUN, LSUN. It's this is really a huge data set. It has like 10 categories, but each category has like an unbelievable amount of samples. So these are generated bedrooms, and like some of them look really good. Like this one looks really good. Like this one, yeah. This is again always on the generated bedrooms, but we can see an interpolation again, right? So I sample here and I sample there and I interpolate through them, and you can see the change from one to the other. The problem is, as we were saying, that the Z space doesn't really represent features, so you never know what is gonna come out when you interpolate between them. Like it represents features, but it doesn't represent features that are usually interpretable by us. Okay? Any questions? Yes.
So, question on these, like to the left and the far right, it's like merging between them. Are those also generated from the sample, or does it not matter? Or like the far left picture and the far right picture?
So, the far left and the far right, you sample from Z and generate, and this is the far left. You sample another one from Z and you generate the far right, but you have the two Z vectors and you interpolate between them and you find each of them.
So could you use like an actual picture though? Or like one of those and then interpolate to like a made up picture? Like
you can, like, so you want to have like a real one here and a real one there.
or a real one there and a fake one there even.
Okay, but you have to find the Z space of the real one.
Right.
Which is like possible, but you have to add more stuff on top of it. Like GANs are actually a very prolific field of research, and so someone actually did that too. For example, there is ByGAN, where you have a generator, but you also have an encoder. So the generator generates from Z to X. The encoder finds the transformation from X to Z, and the discriminator is a function of both X and Z. So basically, the encoder is forced to bring X to a subspace of the Z space that is similar to the space from which we sample, right? So at that point, you can actually go from X to Z, and so you would obtain the Z here, and you can interpolate towards there. But it's not properly what it's called the vanilla GAN, like the one that I just explained. You have to add stuff on top.
Right.
Yes, as I was telling you, like this is kind of the usual architecture of a generator. So we usually use, especially for images, a transpose convolution. Sometimes you find it as upsampling, or like there's different ways people do it. I usually use the the transpose convolution. Someone uses an upsample, that just means, like, let's say that here you have n by n images, right? N by n features. They upsample with like interpolating, right? They use like bilinear interpolation to just make it bigger, and then they convolve normally. Someone does that too. Yeah, I usually use a transpose convolution just because at that point I don't have to go through a step that is not properly learnable, right? It's just what it is. Both the techniques can actually lead to some squares artifacts in the images, especially at the beginning. But since these square artifacts would be a huge red flag for the discriminator, then the generator learns right away to get rid of those. So, okay. The advantages of GANs is that they are completely unsupervised, that they implicitly learn probability distribution, even very, very complex probability distributions. The main advantage is the quality of the images. Especially for images, GANs are the best you can find to generate images, because if you remember, for example, VAE, even if they are very good, they will always give you blurry stuff, right? Then with some tweaks, the discriminator can also become useful as a classifier, but you have to modify it. There are certain disadvantages, while, as I was telling you, they are very, GANs are very, very fussy. Like, if you change a small hyperparameter, it could break really bad. Any of these hyperparameters and even more. So, this is because, right, we are using, since we need a classification, we are using a sigmoid. The sigmoid, if the discriminator saturates right away, right, the derivatives that go towards the generator are almost null, right? So this is the main problem. And the problem is that if at any point the discriminator saturates, the generator degenerates. So sometimes it happens that when I'm training again, right, I see the progression. So I see these images getting better and better and better, and then at a certain point it just gives this kind of stuff, and it doesn't recover anymore. At that point, the discriminator has won, and the generator cannot do anything to go back. So I have to interrupt and start over, and change some hyperparameter at that point. Let's talk for a little bit about mode collapse. So mode collapse is a very well-known and very studied problem of GANs, right? Yes?
So why is GAN more sensitive?
To what? To hyperparameters?
Yes.
Because of this, because it's a game, right? And it's a game that only depends on the discriminator's loss. So if as soon as the discriminator is winning, the generator cannot recover anymore because of the derivatives being flat, right? Plus, it's more unpredictable because of this game. Because when they start from different points in the parameter space, right? You cannot really predict how they will change in respect to the other. While the other, like any other network that is not based on game theory, like you can always kind of predict where it should go, right? Does it make sense? Anyway, so any other question?
One is the deal with the I can't remember the name, detector or whatever it's called.
The discriminator.
The discriminator, right. The discriminator and not necessarily like the generator, just because like the discriminator is easier to model than a generator, or because they both are going to flatten out, right?
Okay, but the discriminator only has to learn what is real and what is fake. The other one has to generate. The task of the generator is way harder than the task of the.
So like it's just like that's what I'm saying. There's just one's easier and one's harder.
Yes.
So that way, why
You usually model them like not usually. Often they are modeled like to mirror each other,
Right.
as like architecture wise, but more often than not, you have to use some trick to like to be a hindrance to the discriminator.
Like weight them kind of like.
More often than not, for example, one very like used trick is okay. At each iteration, you train like twice the generator and only once the discriminator, so that the discriminator only takes one step when the other one can take two.
Right.
But then there are a lot of other tricks that you can use, and like there's a lot. Any other question?
So why don't you say it's the current training state of the game, and then when you are tuning the hyperparameters, when it goes like completely wrong, then you go back to the.
I do. I usually do it. So you know when you can go back. A good thing you could do is if you have a metric to calculate how well the gun is doing, you can actually save it when there is an improvement and avoid saving when there isn't one. That is what I do usually, but yeah, I mean, sometimes, like more often than not, it actually degenerates before reaching any meaningful result. So, yeah. Any other question? Okay. So let's talk for a second about mode collapse. Mode collapse means it is a phenomenon that happens almost only in GANs. I haven't met it in any other generative model for now. But it happens when only one part of the whole real probability distribution is actually generated. Like in this case, you can see that these sevens, they look real, but there's only 7, right? So, this doesn't work, right? Sorry. So, it just means that only, do you all know what a manifold is? It's a mathematical thing. So, like, I learned it when I took, like, image processing too. So,
Set of points or
the manifold is a set of points. Like, it's
set of point. You mean set of point?
Sorry? Oh, a saddle point? No. I mean, the manifold itself, right? Like, you have the whole manifold of the real data. The whole space of the real data. But then the generator only learns, like, this space of the real data, right? Which is a subset of the whole set of the real data. And this is because you can, I mean, I'm writing a paper about this stuff, but it is because of certain properties of the discrimination, right? Because if I keep given the same, if I only learn to generate 7s, right? But 7s are really good. The discriminator will not be able to catch that I'm generating 7s and only 7s because they look really good. They look like real 7s. But the discriminator doesn't really see that, okay, the generator is actually not giving me anything else, right? So this is a problem that has been studied in GANs. It's even like, even here, as you can see, like these faces look pretty legit, right? But the variability between them is almost 0, right? Like all of them have like dark hair, all of them are women, all of them have like very defined lips, Does it make sense? So this is very clear mode collapse. Good samples, but only from a subset of features that you can find in the real data. It doesn't span the whole set of the real data. Questions?
So usually it does that happen because the data. Okay, so to solve this problem, is it good that we just try to feed as diverse data as possible?
That we try to feed to what?
We try to feed the whole gang as diverse real data as possible.
Yes, but the real data, you always use all the real data you have. Right? Like for example, in this case, I am sure that this guy used the whole data set that he had, which is probably Celebay, I would say. Yes. So the discriminator actually saw the whole real data. It's just that the generator, what happens usually is like, if you train, for example, on MNIST, it learns that ones are the easiest thing, like the generator at the beginning tries to model different things, but of course a one is just a stroke, right? On the paper. So it learns that first, and then it learns that it's always penalized when it tries to do anything else. So it does only once. And the ones get really good, but I am actually using the whole span, like the whole data set, to train the discriminator. Does it make sense? Maybe I didn't. Did I understand what you said?
Not quite.
Not quite. Sorry.
No, but that's fine. If I do these things, I can look at the paper.
Okay. Sure.
So any solutions for mode collapse?
Sorry?
Any solutions for this mode collapse?
Yes. Yes, there are some solutions. For example, there is a Wasserstein loss.
A change to the loss function?
There is a change. Someone changed the loss function, and it's actually a very mathematical, like, true thing.
Does it work for you?
It works. Well, I haven't tried it myself. I always work with this kind of stuff, but yes, it actually does, because changing the loss function to the Wasserstein, how can I say, like, it's more of a distribution of thing rather than just a single example. Like, yeah,
I can imagine.
yes.
So does mode collapse have any effect on the quality of the images? So I think it like could go both ways, right? If there is like where it would say, oh, this type of face is really easy to generate, so I can do this well. So
Yes.
I can continue to do that. Or you could also think like there's not much competition anymore, and it could kind of degrade. Is there any kind of effect like that? So like so the mode collapse affect the quality of the images, whereas like
No. The quality of the image, in this case, there's more collapse, but the quality of the image is pretty good,
Right.
right? So no.
Right. I'm just saying, like, possibly, like, where things like, oh, this is a small sample space that I can
Oh, I
generate
can learn
really
better
well.
that subspace. You mean?
Exactly.
No, it's
Yeah.
actually pretty much the same.
Okay.
Just a second. Huh? You? Didn't you have anything?
I was gonna ask whether you encounter this a lot personally in your own research.
Yes.
Really?
Yes. More than I would like to say.
It's like a very serious problem.
Yes. Yes. This is like since the very beginning, people have encountered mode collapse in games. Yeah.
Can you make the generator go from record by visualizing, you know, if it actually produces images of particular subgroup again?
In the end, what happens is, like, from my experience, when you reach this kind of stage, the discriminator starts seeing the, like, okay, dark hair, very like a woman with dark hair with this and this and this, right? Keeps coming, and so since it keeps coming, I will start. The discriminator starts saying, okay, these are fake. Even when they're real, it says they're fake, because to be fair, even if it makes a mistake on that, the probability that it will make a mistake is so small that it's still winning by far, right? And at that point, it just saturates and the generator doesn't learn anything anymore, more often than not. At least from my experience. Some other times, since they are fussy, the generator is not able to learn this, and so it just fails and starts giving like 0.5s. Any other question? Is it clear? Yeah? Okay. So, as I was saying, it's a very active area of research. So someone devises better functions. Others make. There are others that actually change, for example, not only the loss function, but also the z-space itself. For example, the conditional GAN, what it does is I sample at random, but then I attach some label, for example, for MNIST. I attach to the z-space also like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So at that point, the space I am putting something more that will diversify the space, and I avoid this. And plus, I know that at each point, if I want to generate a 0, I can attach a 0. So there are different tricks. These are just some of the papers that came out about GANs in 2017. As you can see, like each of these actually presents a different version of GANs. And it is because GANs are very good with images. And so even if they have problems, we are very reluctant to act like kicking them. We just want them to work. Okay? Yeah. So I think it's over. So just recap. So we saw pixel RNN and pixel CNN that explicitly can model density functions. We saw very small decoders that cannot explicitly do the same thing, but they kind of they found the workaround of just working with the upper bound, sorry, the lower bound. And then we have GANs that cannot give you any real probability, but you can at that point sample from the probability distributions. Yeah, I am done for today. If you have any more questions. Yes.
So, what are the potential applications of GANs? It seems like it's like, oh, it's cool, you can generate images, but how do you?
Yeah, you asked me last time too.
Yeah.
You generate to augment data, for example, because, for example, with ByGAN, you can interpolate from one to the other, right? And so obtain all the span of features that you don't really have.
Okay.
You can do like that. They are used for a lot of things. They are also used, for example, for do you know what adversarial attacks are?
Yeah.
So they're used for adversarial attacks. They're used.
How are they used in adversarial attacks?
You try to generate. Okay, you train a classifier, right?
Okay.
Then you train a network, so to generate feature maps that would basically nullify or make the classification wrong.
Okay, so they're like generating masks essentially.
Generating masks.
Yeah.
Yes. They're used to like improve classification in a lot of different ways.
Right.
Like they're used for a lot of different things.
Is anybody doing anything with not like using GANs that don't have to do with images? Like,
Yeah, I mean, the first time he demonstrated that they work, he demonstrated on a Gaussian, like a 2D Gaussian, so.
right.
Or maybe text.
Sorry?
Using GAN to generate text or other.
Yes. Yes, they are used for text. Like I've seen a few things, but I am in image analysis, so I don't actually look too much into that. But yeah, they're also used for that kind of stuff.
There are some companies that are generating objects for like even cars using it. I've seen that. It is called as generative design.
Yeah, I mean it could be.
If you see the projects by AutoCAD or Autodesk.
Yes. Something that can be read into AutoCAD. Yes.
What would you say?
Generative design or something like that.
Generative design?
Yeah. They're actually creating a model of car or a bike which has not have been designed by first.
Interesting.
Yeah.
I mean, I am in image analysis, but and so for me, images are the things that I usually use. But in this course, we usually use images because images are sorry?
Is it tractable?
They are more tractable, and they are also for people that are starting, images are easier because you can actually see the results right away. If you use other stuff like either more complex or just numerical, is not as easy to read. So that's why we use images, but it's not almost any kind of data can be modeled through GANs. So yeah. Okay. And then
How do they generate a video then?
how do they generate videos? Actually, have you seen
some video fake?
Yeah, have you seen for example what?
I mean, like the Obama video.
Yes, like the Obama video. Have you guys seen that? That is you can generate a video, but you have to tweak it in a lot of. Well, I mean, you can actually, for example, just give as input a sequence of images of the video, and then have it generate a sequence of that stuff, right? So you can do that, for example. I've never tried, but there are a lot of them.
Does that need RNN?
Sorry?
Does that need RNN? Recurrent in network?
I don't think necessarily, but I told you I've never tried, and so I wouldn't know precisely. But yeah, if you give it frames, then the generator has to understand that the frames have to look kind of similar between each other, but not properly, and all this stuff. But it's a more complex problem.
So I'm wondering, how does this exactly works? You have a generative media. Like in CNN, we know that we are updating theta set like weight matrix to guess what is the distribution that the image is coming from, right?
Yeah.
But in generative models, what is the fundamental basic principle behind it? How does it generate images? That's where I'm not very sure about. How does it generate images from? We are providing it a random distributed noise or something like that, right? Okay. And after that, what it does with that frame to convert it into images? That's where.
What, the architecture?
Yes. What's
sorry, I thought I showed you an image. Okay, what I usually do is I take 100, for example, for faces, right? 100 dimensional vector.
Right.
Okay. I process it through some fully convolutional thing, and then I reshape it into n by n by n features.
Right.
Okay.
Yeah.
Then I use these transpose convolutions, right?
Right.
And usually when you use transpose convolutions, you double x, you double y, and you halve the number of features.
Okay.
Okay?
Okay.
And then you go some convolution, then half convolution, well, until you reach, like in the case of faces, like RGB. So you have like n by 3.
Right.
And that's your output.
I see. Okay, so let me see if I got this.
Yeah.
So you have like some vector, right?
Yeah.
Or something like that.
Yes.
And you provide it to the network.
Yes.
So the network converts it into a matrix
Yes.
or a tensor, I would say.
Yeah.
Yeah. And for that, it uses a similar method that is used by convolution neural network, which is
Yes.
opposite,
Yes.
right?
Yes.
So yeah, transposing it.
Mm-hmm.
I would say, yeah, and we are updating weight matrix of that network, which does this transformation, right?
We update the filters that create them.
Filters always.
Yes. Yes. Make sense?
Yeah, makes sense.
Okay.
Thanks.
You're welcome.
I had a question on conditional GANs. When you augment the vector with some label, for example, you'd also have to, if I understand correctly, well, I would assume that you also have to change the loss function to penalize, something that produces something that's not classified as a.
Yes. Exactly.
Okay. But you can still use one. You should be able to still use one discriminator.
Yes, but you can also teach the, like, if you have, in the case of conditional GANs, though, you already have some labels. You have some kind of prior, and so you can actually train the discriminator to also discriminate between the various digits.
Yeah.
Right? And so penalize the generator if actually doesn't.
Yeah.
Right?
Okay.
Mm-hmm.
Yeah.
Okay.
Yeah, just want to know that one of my friends and from the Department of Economics, and he's using GAN to do behavior and game theory research. So because he's researching studying the behavior of human beings, but they don't have enough data points. So they use GAN to generate reasonable behaviors. But the problem they encounter is that the bound class.
Yes.
They find that the behavior distribution is the variance is very, very small.
I know.
Even barely usable.
And is it even smaller than actually the variance in the real data?
Yes.
That is definitely more.
Yeah, the most caps. And well, perhaps today's slides I can share with you.
Yeah, sure.
Good. Well, thank you so much. You did really a great job today.
Thank you. Thanks.
Yeah, a lot better than yesterday, the last lecture.
Yeah, it was pretty. I'll tell you the right word when I stop this.